And when we talked about it, a couple of basic properties were, of course, the expected value of a constant is just the constant. Why is that the case? Because if we plug in, if all the values are the same, what you would get would be all the x values are the same times p of x of I. Since R is independent of I, we know the sum of all the probabilities equals 1. We just get R. So the expected value of a constant is the constant, meaning if everybody gets the same grade on the exam, the class average is that common grade. And then we, in fact, it showed more generally the same result. If A and B are constants, this just turns out to be A times E of X plus B. And if X and Y are two random variables, we haven't proven this yet, we just accepted this for now. This just turns out to be E of X plus E of Y. In fact, one could generalize this if one wanted to, E of, say, A1x1 plus A2x2 and so on. It's sort of a linearity property for expected value. This just turns out to be A1 E of x1 and so on, A sub n E of x sub n. So the expected value is a nice and linear function, essentially. In fact, we're going to show, well, we'll do that a little later, in fact. I think I'll prove it in the next section. Let me just make sure. Well, okay, when I get to it, I'll prove it. And then we have one measure of a random variable, that's the expected value. But I showed you the other day that it's possible for two random variables to have the same expected value, but they can be very different. That is, the distribution around the distribution of the grades they may not be clustered very close together, and yet the average could be the same. So to take care of that, we defined another we defined another measure of central tendency called the variance. And we define the variance to be a special expected value. What it does, it says, look at the difference between the mean and all your observations, square it, and there are two symbols for that. This is called the variance. It measures the difference about the mean, basically, and the reason we squared it is that because if there were no square there without the 2, it would just be 0. And then we showed that using the properties, in fact, maybe it's worth showing once again. So if you actually wanted to compute this, what one can do is the following. One can actually multiply this out. And now use the properties of expected value. So that would give us E of x squared. Remember, the mu is a constant. And E of mu squared. Okay, so what does that give us? Well, that gives us E of x squared minus 2 mu, and E of x is another way of saying mu. And E of a constant is just a constant. So this turns out to be E of x squared minus mu squared. So we have another expression for the variance, an equivalent expression, namely it's E of x squared minus E of x squared. And then I showed the last time, again, this is all putting things back together again, that firstly, V of x plus a constant is equal to V of x. And the reason for that is, you can prove this mathematically using the definition above. But if you think about it, all you're really doing is you're taking all the observations and moving them C units either to the right or to the left. Well, that's not going to change the distribution. literally the variance, the distribution around the mean is going to stay the same. We're just translating everything. And one can prove that quite formally. In fact, I showed you a more interesting result the other day, namely v of ax plus by actually turns out, well, first, before I do that result, let me just state the following. We also showed that v of ax, where a is a constant, turns out to be a squared v of x. We prove that. To prove that very easily, all you have to do is go up to this expression right here, replace x by ax. So what do we get? We get v of ax equals e of ax squared minus e of ax squared. Now that just gives us e of a squared x squared minus a e of x squared, right? I'm just using the properties here. So this is a squared e of x squared minus a squared e of x quantity squared, or a squared times e of x squared minus e of x quantity squared, and just a squared v of x. Remember, this is just v of x. So that's a pretty interesting property. That is, so v of ax plus b is therefore equal to v of ax, the translation property first, and that's equal to a squared v of x. Then I showed something more that I'm not going to do the work again. It's right in the text to you if you want to see it. Suppose you look at v of ax plus by. Well, this is going to turn out to be expanding this. What you do is think of this as being w, and then put it in the formula above. And lo and behold, what you end up with, once I get back here, is a squared v of x plus b squared v of y plus 2ab, I believe I'm remembering this correctly, I'll check it in a moment, e of xy minus e of x, e of y. And that's a pretty interesting result. Let me just remark, let me make sure I copy it right. And I make an observation about that. Where's my, yeah, okay. I want to make sure I remember it correctly. I didn't want to read it right. And this term right here, we're going to give a name in the next section, or a section for that, is going to be covariance of x and y. And sometimes it's written sigmas of x and y. So the following observation, suppose we look at the case. All right, so let's rewrite this one more time. So v of ax plus by is equal to a squared v of x plus b squared v of y plus 2ab times this new term, which I call covariance of x and y. Don't worry about the name. So notice in particular, if a equals b, v of x plus y is just equal to v of x plus v of y plus 2 times this other term. So I want you to understand, in general, v of x plus y is not equal to v of x plus v of y. However, if this term which is equal to the E of xy minus E of x times E of y. Oops. If this term is 0, then v of x plus y equals v of x plus v of y. Well, that means, by the way, something interesting. We're going to show the following result in a little bit. If x and y, whoops, where'd it go? If x and y are independent, and we know what independent means. I can give a fancy definition for two random variables. Then we're going to show, okay, that E of x, y equals E of x times E of y. We have to show this. Okay, it's not obvious. And if this is the case, then v of x plus y will equal to v of x plus v of y. That's pretty cool. But they have to be independent. In fact, we're going to show even more. It's possible for them to not be independent and still that can happen. We'll talk about that a little later on. Okay, so I have these basic properties of variance. And by the way, more generally, if x, y, and w are all independent, then it would happen that this would equal the sum of the variances. But we need to show this. And I think I sort of want, that's about as far as I went the last time. Yeah, okay. So somebody had a question about homework?
Yeah, Professor, I did.
What was the question?
It was number 4 on page 114, section 2.7.
Okay, let me find it. Determine the expectation, variance, and standard deviation of the random variable exercise 4 and 2.6. So let me go find
Yeah.
that 2.6, exercise 4. Why can't I find it? Okay. Suppose a pair of fair dice are tossed. X is equal to the maximum number that shows up, and y is the minimum. So suppose 2 dice are tossed. X is the maximum of the top numbers and y is the minimum. Determine the range and give the, okay. So let's understand this question. So we toss a pair of dice. X is the maximum. So what are the possible values if I toss a pair of dice?
If you toss a pair of dice and you get the maximum, you only get like 6 and 6 for.
So hold on. First, I need to understand this question for a second. Suppose a pair of dice are tossed. So the maximum could be 1 through 6, couldn't it? As if you toss a pair of dice, is it possible to get a 1 and a 1?
But wouldn't that be the minimum?
But it's also the maximum too. So one possible value is 1. Another possible value is 2, up to 6. Wouldn't that be the case? Can any of these numbers be the maximum? What are all the possible values for the maximum? If you toss a pair of dice, I could get a 1-1, couldn't I? Then 1 would be the maximum. If I got a 1-2, then 2 would be the maximum, and so on. If I got a 6-5, 6 would be the maximum. So what's the probability that I would get a something's bothering me about this problem. I'm trying to understand what's bothering me, but hold on. So one more time, look at it. Suppose a pair of dice does maximum of numbers pairing on top. So what's the probability that the maximum, if I toss a pair of dice, that the maximum will be a 1? What would that be? Well, how many ways can the only way the maximum can be 1 is if you got a 1-1, correct?
Correct.
So that would be 1 out of 36. Yeah. You know, I something about what am I asking you to find here? Well, I'm doing problem number 4 first. Okay. What about how could the maximum be a 2?
You could get a 1 and a 2, then you get a 2 and a 1.
Okay, is there any other way? If I got anything else, what would happen? So the only way the maximum can be a 2 is if I get a 1 and a 2, a 2 and a 1, or a 2 and a 2. Yes?
Yeah.
So that would be what, 3 out of 36? What about a 3? In order to get the maximum to be 3, what can I get? I can get a, in order for the maximum to be a 3, I can get a 3-1, a 3-2, a 3-3, a 1-3, a 2-3. Did I count them all? In each of those cases, the maximum would be 3. What was that, 5?
Yeah, that was 5.
All right, keep me honest, guys. In order for the maximum to be a 4, I get a 1-4, a 2-4, a 3-4, a 4-4, a 4-1, a 4-2, a 4-3. Did I get them all?
Yeah, so that'll be 7 out of 36.
All right. Because I'm doing this in my head, so keep me honest, please. In order for the maximum to be a 5, you get a 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, right? How many was that?
I think that was
that
I think
10?
that was 10. Yeah, that was 10.
In order for the maximum to be a 6, I get a 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. How much was that?
Can you repeat that? Sorry.
Let me do that one more time, okay? I get a 1, 6, a 2, 6, a 3, 6, a 4, 6, a 5, 6, a 6, 6. That's 6 so far. Or I can get a 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. What was that, 11?
Yeah.
Let's make sure everything adds up to 11 and 10 is 21, 21 and 12, 31, 31 to 3, 33, 34. I just got 37. Maybe I had it wrong.
I think 5
5.
is 9, Professor. 9 out.
One?
5,
5 is 9. Yeah.
yeah.
Notice they're all increasing by 2. So there's a distribution for X. So I got the, and similarly for Y. Now, what do I want to do in the other problem? I'll do the Y. I may not either. Let me just see. So we're asking about problem number 4. Determine the variance and standard deviation for the random variable. Okay. So the other part, defining Y, the minimum is very similar. So now let's suppose I want to find the expected value for X. It would just be what? It would be 1 times 1 over 36 plus 2 times 3 over 36 plus 3 times 5 over 36 plus 4 times 7 over 36 plus 5 times 9 over 36 plus 6 times 11 over 36. Somebody sum that up for me? Somebody do that? Well, so now we have the answer for the expectation, correct? Now, if I want to find a variance, what I'm going to do is I'll use the formula E of x squared minus E of x quantity squared. And by the way, that's the answer we just have up here squared. So first I have to compute E of x squared. So the square is going to be 1, 4, 9, 16, 25, and 36, right? That's what's going to happen if I look at the x squareds. This is x squared. And the probability is still the same. So E of x squared would then be 1 times 1 over 36 plus 4 times 3 over 36 plus 9 times 5 over 36 plus 16 times 7 over 36 plus 25 times 9 over 36 plus 36 times 11 over 36. So this is going to give me some number b, right? So the variance would just be this number b I just computed minus the answer I got before squared, whatever that number that was. So it's just a matter of sitting down and doing the computation. Okay, does that answer your question? I didn't do the arithmetic. I assume with the calculator you can do it pretty quickly. Does anybody have a question about this calculation? And the doing the minimum is the same kind of argument. Just look at the case. Were there any other homework exercises that bothered anybody at this point? I haven't finished the section yet, but we can talk about this in a moment. Okay, if not, we'll continue. Now, something I haven't proven yet, okay, is I need to show, and I'm not ready to show it just yet, okay, that is if X and Y are independent random variables, and I'm not giving a fancy definition right now for what I mean by two random variables being independent, but it's clear that X and Y don't affect either one. Then the remark I made before was E of X, Y is equal to E of X times E of Y. If they're independent. And that implies that then V of X plus Y, which is what we said before, is equal to V of X plus V of Y. So this is a theorem to be proven. In fact, I'm going to prove even more. More generally, if X and Y are independent, any function of, what do I say, of these random variables, of their product, is going to equal to the product of the individual . For example, I haven't proven this yet, but I'm just stating it. For example, if X and Y are independent, and this is not chosen at random, E of E to the TX times E to the TY, as an example, Notice this is the function of x. Here's the function of y. You're going to see that this is just equal to e to the e to the tx times e to the e to the ty. Now, I didn't arbitrarily choose these exponential random variables. It turns out shortly we're going to talk about something called a moment generating function, and this will illustrate that very, very nicely. Okay. Now, another idea or two. So I'm just looking at properties of expectation variance. I want to talk about standardization. Okay. So suppose I give you a random variable x, okay? And let's suppose this random variable has mean e of x, which you can just call mu if you like. And its variance is, I'll just call it sigma squared for short. So I give you a random variable. I give you its mean and its variance. And what I want to do now is I want to create a new random variable, which I'll call x star. Okay. Such that x star is linearly related to x, but its mean will be 0 and its variance will be 1. Okay. Well, how do I do that? So I can give you the answer and work backwards, or here, maybe I'll do it both ways. Claim x star is nothing more than x minus mu divided by sigma. That is, this says take any random variable. If its mean is mu and its standard deviation is sigma, if you make this change of variables, then I claim that this new random variable, which I'm calling x star, will have mean 0 and will have variance standard deviation 1. The proof of that is really very simple. Let's look at e of x star. It's equal to e of x minus mu divided by sigma. Well, remember, e of ax is ae of x. So I can take the sigma out. So I get 1 over sigma e of x minus mu. But this is equal to 1 over sigma e of x minus mu. This, of course, is mu. So this whole expression is 0. So we get 0. So e of x star I just showed, this new random variable has mean 0. Now, in the same way, we want to find v of x star. Now, that's equal to, by the way, remember, v of ax is a squared v of x. Let's not forget that property. So this would be v of x minus mu over sigma. If I take the sigma out of the denominator, I get 1 over sigma squared times v of x minus mu. But v of x minus mu is just equal to v of x. But v of x is equal to sigma squared. So I've just shown that v of x star equals 1. So sigma of x star is also 1. So this says something really important. It says if you have any random variable, you could transform this to a linearly related random variable, essentially a random variable the same type, as we'll see, except that this new random variable will be standardized in the sense that its mean is equal to 0 and its standard deviation or its variance is equal to 1. Now, you're going to see that's important when we study the normal distribution to know that fact. Sometimes, here's a typical problem. And then I'll look at a specific example. Suppose you're given a random variable x, okay? And y is some function of this random variable x. How do you compute ey and dy? How do we do that? So let's look at an example. Well, something's wrong with these glasses of mine. I think it's time for a new pair. Okay, so where's my example? I have a couple of examples here. So let's suppose I give you the following distribution, okay? Here's x of I, and it takes on the numbers -2, -1, 1, 2, 3. And the corresponding probabilities are 0.25, 0.20, 0.15, 0.30, and 0.10. And let's suppose I have the following rule: y sub I is equal to x squared. So I'm making a change of variable. I want to find ey. Maybe we'll do it a couple of ways. Okay. Okay, so what are the possible values for the y's? What values will y take? What's the range for this random variable y? Anybody? Well, if y is equal to x squared, when x of I is equal to -2, what am I going to get for the corresponding y sub I?
4.
I'm going to get a 4, right? And the probability that that will happen will be 0.25. When else will I get a 4? I'll also get a 4 when x of I is 2, right?
Yeah.
And that would happen with probability 0.30. So that's equal to 0.55. Okay, what's the next possible value for y? Well, it could be 1, right? -1 squared would be 1. That probability is 0.20. And 1 squared is 0.25. So I've taken care of the -1 and the 1. And what's the last value y could be? 9, right? And that would happen with probability. Something's not right here. My numbers. 30 is 55, and 45. That will happen with probability 10. But my numbers are good. So let me just make this look a little prettier. Y sub I, take on the values 1, 4, and 9. And the probabilities would be, 1 would be 0.45, 4 would be 0.55, and 9 would be 0.10. And by the way, notice the probabilities all add up to 1. So what I could do is now I can find e sub y. It would be 1 times 0.45 plus 4 times 0.55 plus 9 times 0.10. And if I do that, I do the arithmetic here. It turns out to be 3.45. Okay. Now, I want to make an observation. Do I make the observation here? Notice, by the way, that what I did here is I looked at y is equal to x squared, and then I computed for which values of y correspond to their probabilities. But now I want to claim something else. I want you to observe that if we looked at this problem, what happened, really what we did is we took -2 squared, and that happened with probability, where was it? 0.25. I want to go back to these numbers, and then I took a 2 squared, and that was what, 0.30?
Yes,
And then I went with a -1 squared. In that case was -1 was 0.20. And then I took a 1 squared, and what was 1? The probability for 1 was 0.25. And then there was just a single one of plus, what was it, 3 squared times, what was that probability, 0.1? So notice what happened was, for the -2 squared, in these two cases, essentially I got 0.25 plus, what was that, 30? Plus 30. And then for the -1 squared, I got, what was it? Where were the numbers? I lost my place. The numbers were 20 and 25. And then I got 3 squared. So if you look at this, which by the way, I just rewrote what I had above. Notice what's happening here is this is one of the x values squared times corresponding x values. That's what this term corresponds to, right? X of y was either +2 or -2. And here I had another one of the x values squared times the sum of its probabilities, and so on. So the point I'm trying to make is, it turns out that E of y, remember y was x squared, is just equal to E of x squared which means I can just replace it by x of I squared times P of x of I. By the way, this is called Lotus, the law of the unconscious statistician. So this says the following: if you want to find E of some function of x, all you have to do is make this replacement to find the expected value. So again, I'm going to don't have to do that. Say E of your grandmother basically is just replace x by h of x. Over all possible I values. As you can blindly substitute into the equation and get the required result. Do I want to make another observation here? I think there's one more observation I want to make. Oh, where is it? Well, I think I'm going to make this last observation when I need it. This is conditional expectation. I don't need to talk about that just yet. Okay, So I finished what I wanted to talk about in this section, in section 2.7. I don't think that's going to affect many of the homeworks, but I think it's, was there one I wanted to do here? Let me see. Oh yeah, here's an example I forgot to do. This one just illustrates the properties as well. So suppose I give you the following. Suppose I tell you that I have a random variable, e of x is equal to 20. V of x is 3. E of y is 15. So we have two random variables. V of y is equal to 2. And then I ask you the following. I want you to find e of 3x minus 2y plus 5. And B, if x and y are independent random variables, find v of 3x minus 2y plus 5. And you'll see where these come about in a standard way. Well, I claim this is a trivial problem. If we use the properties of expected value, this first expression becomes 3 times e of x minus 2 times e of y plus 5. E of x is 20. E of y is 15. So what does that give me? 60 minus 30 is 35. Is that what I got? Okay. Now, in part B, this becomes v of 3x minus 2y. Remember, because the translation doesn't affect the result. And this is equal to, since they're independent, this is going to be v of 3x plus v of minus 2y. I was able to break this up this way because they're independent, remember, x and y are independent. So any function of x and y are going to be independent. This becomes 9 times v of x plus 4 times v of y. Remember, use the squaring property. And I give you v of x and v of y. Is that what I gave you? V of x is 3 and v of y is 2. So this is what I say, v of x was, v of x was 3 plus v of y, which is 2. 27 and 8 is also 35. Okay. I want to make sure I got everything I wanted here. Okay.
Professor,
Yes.
I have a question. In this B example, we had +5, but why? Because they are independent, we skipped it?
No, because e of, say, ax plus b is equal to a times e of x plus b. Remember, if you add the same number to the expectation, that has the effect of adding that number to the entire value. If you change every value of x by the same amount, that boosts up e by that same amount.
Okay, thank you.
Okay, so again, e of ax plus b is equal to a e of x plus b. On the other hand, v of ax plus b is equal to v times a of x, which is a squared v of x. That's the property of expectation. And versus variance. Variance is always a positive number, by the way. That's another thing to observe. Okay, so all this section did basically was to show you how to manipulate expressions involving variance and expectation. It turns out they're done in a real nice way. Notice the independence of this problem was important because if it were generally, the result would be a squared v of x plus b squared v of y plus 2ab, well, what I call the covariance. This term is what's called the covariance. But since they're independent, this term is zero because they were independent. When they're not independent, you got to worry about this middle term. Maybe I should mention, how's my time doing here? Yeah, maybe I should mention the following. Suppose you have an expression like this. How would you do this problem? Well, if I were doing this problem, what I do is I would call this for a moment W. And then I would say, okay, V of AX plus W. Then this would be what? It would be A squared V of X plus 1 squared V of W plus 2A times 1, what I call covariance of X and W, this other term. And then now what I would do is I would take W, and I would replace W by BY plus CZ. I'm not doing it now. I think I'll work out in the text for you a little later. So what you'll end up getting with something like A squared V of X plus B squared V of Y plus C squared V of Z. And then you're going to get all possible cross terms. You're going to get plus 2AB covariance XY plus 2AC covariance XZ plus 2BC covariance YZ. Well, we'll see this a little later on, but things can get complicated with these expressions, but you just deal with them two at a time and it works out very easily. I will be coming back to this idea soon, but not just yet. Now, let me tell you what students don't like. They don't like this topic, which is called the some theory. And by the theory, there are two theorems. One is called Markups Theorem. Sometimes it's spelled with a double F. And the other one is called Chebychev. Two very important Russian mathematicians. And let me just tell you what the first one says. I'll have to prove this for you in a moment, but one should see this. What these theorems do is they give you two estimates on probabilities. In fact, let me state Markups theorem as follows. Markups theorem says the following. Suppose X is a non-negative random variable. That means the only values that X can take are 0 or positive numbers. Okay? By the way, some books say it differently. Some books say the probability that X is greater than or equal to 0 equals 1. That's how some books state it, okay? Suppose X is a non-negative random variable, or equivalent with the probability that X takes on the value 0 or positive integer is 1. Okay, and let C be some number greater than 0. I better use the same notation I use in the book. Let me read it. Then the probability that X is greater than or equal to C will always be less than its expected value divided by C. Okay. So C is any real number, any real positive number. So this is the probability that X will exceed this value C will always be less than the expectation divided by C. Now notice, I don't give you very much information about X. All I do is I tell you it's non-negative. And then I can give you an estimate on the probability that X exceeds some number C. I'll do an example a little bit. Now, this is a pretty crappy estimate, okay? And why would you expect it to be crappy? Because I don't give you much information. There's a general rule of mathematics, is the less information you have, the less accurate your result is going to be. So notice here, all I told you was that X is a non-negative random variable. Then I can give you an estimate that the probability that X exceeds a certain value will always be less than its mean divided by C. I'll illustrate this in a moment. First, let me prove the result, okay? So how do we prove this? Well, it's a pretty neat trick. We define a new random variable y. And here's how we define y. We define y to equal to one of two numbers. It's either equal to 0 if X is less than or equal to the number C, and it's equal to the number C if I think I want straightly less than here, and this X is greater than or equal to C. Okay. So notice the probability that y equals 0 is equal to the probability that X is less than C, and the probability that y equals C is equal to the probability that X is greater than or equal to C. So I've defined these equivalent events. Now, if we look at this new random variable y, E of y is equal to, therefore, 0 times P of y equals 0. Plus C times the probability that y equals C, or 0 plus C times probably y equals C is the probability that X is greater than or equal to C. So let's see what I have here. I have E of y something's bothering me. What's bothering me? My inequality isn't right. Is equal to, or everything's good. C P of X greater or equal to C. Now notice in my definition, I should remark that X is always greater than or equal to y. look at my definition up here. If X is less than C, Y is 0. And if X is greater than C, Y is equal to C. So the random variable X will always be larger than the random variable Y. So we expect, therefore, that, this would imply, there we go. This implies if X is always greater or equal to Y, then the expected values will be in the same way. So E of X is greater than or equal to E of Y, but E of Y is equal to C times P of X greater or equal to C. So let's look at these two pieces. So this says the probability that X is greater than or equal to C. Where's my directional inequality? Is less than or equal to E of X divided by C. Remember, C is positive. Okay, so that's Markups inequality. Now, I think I have an example of this right here. Oh, where's that example I made up? I made up a really neat example. Yeah, here's an example. This will be in the next edition of the book. I just made this up yesterday. Suppose I toss a pair of fair dice. Okay. And suppose I let X equal to the sum of the faces. And I want to, we know, by the way, I've already done this, that we showed before, if you toss a pair of dice, the expected value, the expected sum is a 7. And the variance, which I'm going to need a little later, is 35 divided by 6. And if you want to see the calculation of this, look at page 111. I worked this out for you the last time. Now, suppose I ask, estimate the probability that X is greater than or equal to 10. I just want to show you it's a crappy estimate. Well, we know, according to Markov, this would then be the probability X is greater or equal to 10 will be less than or equal to the expected value of X over 10. The expected value in this problem is 7 over 10. Which is 0.7. All right. So Markov estimate would give you an answer of, whoops. Now, this isn't a very good answer. That's going to be my whole point here, because the actual answer would be the probability X is greater or equal to 10 plus 11 plus 12. And did I work these out? I think I worked them out already, so I don't have to put it down. The probability X is equal to 10 is 3 out of 36, right? That would be a 6, 4, a 5, 5, and a 6, 4, a 6, 4, a 4, 6, and a 5, 5. 11 would give me 2 out of 36, and 12 would give me 1 out of 36, And this exact answer would turn out to be 1/6 or 0.167. So I want you to understand that this is a pretty crappy estimate because Markov gave us an estimate of 0.7. It said the probability that x exceeds 10 is at least 0.7, is less than 0.7. Well, it's true, it's less than 0.7, it's actually 0.167, but look how off the answer is. So Markov said the estimate is the probability that x is greater than or equal to 10 is less than 0.7. In fact, we know the answer turns out to be 0.167, which is certainly less than 0.7, but it's not a very good estimate. And why would you expect it to be a good estimate? All you were using was the expected value. I didn't give you any more information about the distribution except its expected value. So the point I'm trying to make is when somebody gives you an estimate like this based on very little information, you can't expect the estimate to be very, very powerful. Okay. So what happens is we improve the estimate by looking at another inequality, which I'll just tell you about. I don't have time to develop this yet. It's going to take me about 20 minutes to do it. There's another inequality called Chebychev's inequality. And again, both Chebychev's inequality and Markov's inequality are only useful for the most part for estimates, for theoretical estimates. They're really not very powerful tools, but they enable us to get certain results that would otherwise be difficult for us to get. So even though they're rough estimates, they still work out pretty nicely. So let me tell you about Chebychev a little bit. I won't have time to fully go into it. And you got to be a little bit careful. So let me tell you what Chebychev says, at least. Okay. So what are we giving? So x is a random variable. Okay. It has mean mu and variance sigma squared. Then, for any number a, for any positive number a, I can state it a couple of ways. Let me just talk about this one for a moment. This is one version of Chebychev's theorem. I'll give you a nicer version in a second. Okay. So Chebychev's theorem says that the probability that any observation differs from its mean by a certain number, in this case a, will always be less than or equal to the variance divided by this number a squared. Another formulation of this, by the way, is if take k, let k sigma equal to a. That is, choose a to be k times sigma, where k is an integer. Then this would become the probability that x differs from its mean by k sigma less than or equal to sigma a squared. This would then become k squared sigma squared. This is another formulation. I need to talk about this. I just gave you the result, but I want you to look at this and see what it says. I have to prove this to you in a couple of seconds. Most people like to say it this way, but it doesn't make a difference. You can say it 4 different ways, the theorem. Look what this says. This says the probability that any observation differs from its mean by k sigmas, by k standard deviations, is always less than or equal to 1 over k squared. Now that's an interesting result. Where does it come from? What does it mean? So this is a refinement basically of Markups theorem. I'm going to show you next time using Markups theorem, I can prove this result, and then I'll illustrate this result in certain results and then show you the weakness of this theorem. Just notice what's happening here is it has to be sort of symmetric about the mean in some sense. So what do you do if it's not symmetric? The answer is you got to be very clever. But we're going to show using this result that our original intuition about distributions or probabilities in terms of relative frequency makes a lot of sense. So again, I guess how many of you had statistics already? A basic course in statistics. Nobody had statistics? Stat 2000 the equivalent?
That's
Okay, well, if you did, typically what a typical kind of problem in statistics is you look at the normal distribution, whatever that means. Don't worry if you don't know what I'm talking about just yet, you will. So here's a typical normal distribution. Here's how your data is distributed, say. And here's our mean right here. It's centered around here. And let's suppose this is one standard deviation. We're going to discover that for a standardized normal distribution, roughly 68% of all the data lies within one standard deviation of the mean. So if this is the mean, here's one standard deviation we're going to see between A and B, between these two lines, roughly 68% of our data will lie. And we're going to see, in fact, between two standard deviations, roughly 95% of the data is going to be distributed. And almost all the data will be distributed within 3 standard deviations of the mean. So what this is looking at, what this Chebychev's result is looking at, it's looking at what's the probability that the data is distributed within k deviations of the mean. So for example, we're going to discover for a normal distribution, within 2 standard deviations, the result's going to be about 95% of the data. Whereas if we try to do that using Chebychev's inequality, we'll see the answer is only about 60% or 70%. It's off considerably. It's consistent with the theorem, but it doesn't give you an accurate result. But we need to understand the importance of this theorem. So at this point in the next section, just finish the homework problems in the previous section, but just read Chebychev's theorem and Markups theorem. And the next time I'll walk through a couple of examples and I'll show you the importance of these theorems in proving some other things in probability theory. Let me just make sure I covered all I wanted to cover today. Okay, that's pretty reasonable. If you're confused about Chebychev's theorem and Markups theorem at this point, you should be, because it's not clear yet. I need to consider some more examples. So we'll come back on Wednesday. I'll look at some more examples of Markup and Chebychev, and then we can sort of dispatch the theory a little bit and get back into solving some problems. Anybody have any questions about any of this? I expect it to be a little bit vague right now, with more clarity occurring after you read the material. And you're back here on Wednesday when we'll go over some more examples. Let me just stop the recording. And
Recording stopped.
Let me get back to the screen.